Good day. Today, we'll be talking about chemical kinetics. In this chapter, we'll explore in detail how reactions work, what are the factors that affect the rate of a reaction, and how we can use this knowledge to control chemical processes. Photochemical smog consists of various nitrogen oxides, ozone, and some small organic molecules. Smog is created by the interaction of sunlight with nitrogen oxides from vehicle exhaust and the volatile organic compounds from man-made sources. The conditions that led to the formation of smog and the rate at which these compounds form depend on chemical kinetics. We define the area of kinetics as the study of the rates of change of concentrations of substances involved in chemical reactions. Consider the various reactions involved in the creation of a photochemical smog. The first reaction takes place within the internal combustion engine and involves the reaction between nitrogen and oxygen to form nitrogen monoxide. This reaction is highly endothermic, but the high temperatures within the combustion engine makes it possible for this reaction to proceed. In the second reaction, nitrogen monoxide produced within the engine is released to atmosphere, where it combines with oxygen to generate nitrogen dioxide, the brown gas commonly associated with the smog. Note that this reaction is exothermic and therefore energetically favorable. Delta H for this reaction is actually smaller than 0, or exothermic. In the third reaction, sunlight provides the energy to break bonds in nitrogen dioxide to form nitrogen monoxide and oxygen atoms. These oxygen atoms can then combine with oxygen to form ozone, or it can also react with water to form OH radicals. The OH radicals are highly reactive species that can react with volatile organic compounds to form other substances such as peroxyacetyl nitrate. Note that these reactions are linked. Products of one reaction also serve as reactants in another reaction. As a result, the system is very complex. In order to understand the phenomenon of photochemical smog, we need to understand the relationship between each of the individual reactions, as well as the factors that will affect how fast a given reaction may proceed. In the reactions involved in smog formation, the products of some reactions are the reactants in others. Therefore, the relative rates of these reactions influence at what time during the day pollutants appear and how long they persist. Note in this figure, for example, the maximum concentration of nitrogen monoxide occurs during morning rush hours. As nitrogen monoxide is converted to nitrogen dioxide, the concentration of nitrogen dioxide increases and the nitrogen monoxide decreases. Later in the day, sunlight breaks down the nitrogen dioxide to form free oxygen atoms, which then react to form ozone. That's why ozone concentration increases during the afternoon. The catalytic converter, which is now standard feature on automobiles in this country, has helped to minimize the problem of photochemical smog by removing nitrogen monoxide from exhaust gas. Knowledge of chemical kinetics has made it possible to create catalytic converters and other devices that can be used to improve air quality. We define chemical kinetics as the study of the rate of change of concentrations of the substances involved in a chemical reaction. And the reaction rate is how rapidly a reaction occurs, which is related to the change in concentration of a reactant or product over time. Reaction rates are affected by several factors: physical state of reactants, concentration of reactants, temperature, and the presence of a catalyst. About the physical state. Generally speaking, reaction rates are faster for substances in the liquid or gas phase than in the solid state. Concentrations of reactants. The more collisions there are between the particles, the more likely an interaction will lead to reaction. As interaction increase, the interactions between particles will increase. When temperature increases, the average kinetic energy of the particles and the collisions between particles will increase. As the rate of collisions and the collision energy increase, the likelihood of the reaction increases. Catalyst. The presence of a catalyst tends to increase the rate of a chemical reaction. We'll explore each of these factors individually. Let's return to the reaction between nitrogen and oxygen that we introduced at the beginning of the chapter. The amount of nitrogen monoxide formed in a given period of time depends on how fast the reaction proceeds. We can define the rate of the reaction in terms of change in the concentration of the product. The change in concentration can be calculated as the final concentration minus the initial concentration. Since nitrogen oxide is the product, the concentration of which will increase over time, so the difference of this final and initial concentration will be positive. The rate of change in terms of nitrogen monoxide will be positive as well. Alternatively, we can express the reaction rates in terms of the rate at which a given reactant is consumed. Alternative expressions for the rate of consumption of nitrogen and oxygen are shown in this slide as well. In all cases, the rate is expressed in terms of change in concentration of the reactant as a function of time in terms of a reactant. But please note, because nitrogen and oxygen being the reactants and being consumed in the process, the final concentration will be smaller than the initial concentration. So the change will be a negative number. So that's why we put a negative sign before the whole term. So the rate based on the change of nitrogen or oxygen will be positive. The rate of change sometimes is also specifically referred to the rate of disappearance for the reactants, the rate of disappearance for the reactants, or the rate of appearance of the product. Please also note these rates are going to be different if the chemical coefficients or the number before each term is different. For example, for every molecule of nitrogen or oxygen being consumed, twice as much nitrogen monoxide will be produced. So the rate of change for nitrogen oxide will be twice as big as that of the nitrogen or oxygen. The rates of the disappearance of the reactants and the rates of appearance of the products, or sometimes it's called the relative rates of the consumption of the reactants and the formation of the products, are based on their chemical coefficients, so they can be different. The reaction rates are standardized by multiplying the inverse of the chemical coefficients based on the corresponding rates of change. For example, nitrogen has a chemical coefficient of 1, so the inverse of that chemical coefficient times the corresponding rate of change is defined as the reaction rate. It can also be defined based on oxygen, which has 1 as the chemical coefficient. So the inverse of that chemical coefficient times the corresponding rate of change based on oxygen. It can also be defined based on the product, which has a number 2 as the chemical coefficient. So the inverse of that 2 times the corresponding rate of change. These rates will be exactly the same after they multiply the inverse of the corresponding chemical coefficient. We have more examples in the problem set. Suppose we ran a reaction in the laboratory to determine the rate of the reaction between nitrogen and oxygen. We can express the rate either in terms of the rate of consumption of nitrogen or oxygen, or in terms of the rate of formation of nitrogen oxide. We can also determine the reaction rate based on the standardized rate of consumption or rate of formation. A typical set of concentration data for these species are presented in this table and are graphed in figure on the right side. As expected, the concentration of the reactants decreases and the concentration of the product increases as the reaction proceeds. If we look at the change in concentration for nitrogen monoxide between 5 and 10th microsecond, we can calculate the rate by noting the change in the concentration over time and obtain the rate of 1.4 molar per second. Similarly, if we define the rate in terms of change in nitrogen over the same time interval, we calculate a rate of 0.70 molar per second. This is expected because twice as many nitrogen monoxide is produced while 1 molecule of nitrogen or oxygen being consumed. The rates calculated in this manner represent so-called average rates because they are based in a period of time. In a different time period, the average rates will be different because the corresponding concentrations will change differently. As we learned previously, the average rate can be calculated based on the change of concentration divided by change in time. For more example of detailed calculation, please refer to the problem set. We can also determine an instantaneous rate of reaction as the tangential slope of the concentration plotted versus time. This is illustrated on this slide for the reaction. The change in concentration of oxygen over a specific time interval can be used to calculate the average rate of consumption of oxygen during that time interval, but can also be used to determine the instantaneous rate at the midpoint of that time interval. We simply do the slope of that point of time. The instantaneous rates can be seen more clearly as the tangential slope in this expanded section of that oxygen curve. Using the change in concentration between 1000 and 3000 seconds to calculate the slope at that point of time. In this way, the reaction rate at a particular instant can be calculated. The key is to find the slope at that particular point of time. Let's look at one example. In this example, we are asked to calculate the average reaction rate for the time period between the 15th second and 30th microsecond using the data below. Using the data from the table, we can calculate the rate either as the rate of formation of nitrogen monoxide over the stated time interval, or as the rate of consumption of nitrogen or oxygen. Reaction rate is defined as the change in concentration over time multiplied by the inverse of the chemical coefficient. We can do the calculation of the reaction rate based on the formation of nitrogen oxide. So it's the change of concentration divided by the change in time. After we do the calculation, we have the rate based on the formation of nitrogen monoxide. To do the calculation in terms of the consumption of nitrogen or oxygen, we have to put a negative sign before it, because the rate is decreased. The final concentration is smaller than the initial concentration. And the change of time is also from 15th second to 30th second. In this calculation, we also find out the rate based on the consumption of nitrogen and oxygen. They are 2.7 times 10 raised to 5th power molar per second. As you noticed, this rate is only half of that based on nitrogen monoxide formation. This is indeed expected because the chemical coefficient for nitrogen is 1, for oxygen is also 1, which is a half of that of chemical coefficient for nitrogen oxide. The calculation is consistent with the stoichiometry of the balanced chemical equation. The rates based on different substances is related to the chemical coefficients. In the previous section, we examined how we could calculate both the average reaction rate over a specific time interval and the instantaneous rate as the slope at the given point. Consider the concentration data plotted in this figure. The tangential slope of the curve at the points B and C represents the instantaneous rates at the specific times in the reaction. The slope at the point when time is 0 is known as the initial rate. Clearly, the reaction rate decreases as the reaction proceeds. Eventually, we can imagine that the rate of change could approach 0, at which point the concentration of reactants in the products no longer change. This behavior is typical for most reactions. The most rapid reaction rates occur early in the reaction, and the reaction rates decrease over time because the concentration of the reactants will decrease. Exactly how reaction rates depend on the concentrations of the reactants, however, is not always obvious. If we double the concentration of one reactant, the reaction rate may also double. If we double the concentration of another reactant, however, the reaction rate might quadruple. We need a way to determine the nature of the dependency of rates on concentrations of reactants. Experimental observations and theoretical considerations tell us that the reaction rate depends on reactant concentrations, but they do not tell us the exact dependency. Based on experimental data, we can determine the nature of this dependency and express it as reaction order, a parameter that tells us how a reaction rate dependent on the corresponding concentration of a reactant. Knowing the reaction order also provides insight how a reaction might proceed on the molecular level. For example, which molecules must collide and which bond must break in order to form the observed product. We can summarize the relationship between the reaction rates and the concentrations of reactants using so-called rate law. which is a mathematical relationship that defines the experimentally observed relationship between the rates and the concentrations. A rate law can be mathematically expressed as this, which tells you the rate is dependent on the reactant concentration, and the K is the rate constant. M and N are the reaction order with respect to the corresponding reactants A and B. For example, if a rate law is expressed as K times A raised to 2 and B raised to 1, then we can say the rate order or reaction order with respect to concentration A is 2, and the rate order or reaction order with respect to B concentration is 1. And the overall reaction order is M plus 1, is the overall reaction order or rate order, which is 2 plus 1, which is 3. Overall reaction order is 3. Please note the values of M, N, and the rate constant K must be determined experimentally. How do we design experiments to determine the reaction rate law? Let's study the reaction between oxygen and the nitrogen monoxide to form nitrogen dioxide. We can write a generic rate law. The values of M and N can be determined experimentally by observing how the initial rate of the reaction changes as the initial concentration of the reactants is systematically changed. Consider the reaction in this table. That the initial concentration of NO is the same for trial 1 and 2, while the concentrations for oxygen changes between experiments 1 and 2, and the initial rate changes accordingly. Similarly, the initial concentration of O2 changes. For O2 stays the same for experiments 1 and 3, then the concentration for NO changes between 1 and 3. In both cases, for example, in experiment 1 and 2 and experiment 1 and 3, you keep one concentration changing and the rest of concentration kept constant. Then the rate change must be the result of the change of that one change in concentration. Let's look at the details, how we use the information to determine the reaction rate law. To find M, the reaction order with respect to O2, we need to compare experiments 1 and 2, because in those two experiments, oxygen concentration changes, while the NO concentration does not change. As you can see, when the concentration of oxygen is halved, the rate is also halved. So for this reason, the rate is directly proportional to the O2 raised to M. And here, apparently, the rate changes as many times as the oxygen changes. So M is 1. Similarly, to find N, we need to compare experiments 1 and 3, because experiment 1 has oxygen concentration at the constant. The only change is NO concentration. As we can see, when NO decreases by 2 times, from 1 to 3, the reaction rate decreases by 4 times. So for this reason, the rate change is directly proportional to the concentration change squared. For this reason, the N, or the reaction order with respect to NO, is 2. So you put this together, rate will be K times concentration of O2, which is raised to 1, that 1 is not written, times NO concentration raised to 2. And this K can be calculated from the rate law using the data for any experiment. For example, if we substitute situation number 1, rate for the first situation is 1.0 times 10 raised to negative 6 equals that K, and the concentration, so we can substitute the concentration O2 over here. O2 is 0.0100, as you can see in the first experiment over here, times, then it's NO squared. We substitute the NO concentration to over here. NO is 0.0100 squared. Then we can calculate the K. K equals 1 mole. Hopefully, through this example, we have learned how to design experiments to experimentally determine the rate law. The key is for any 2 experiments, you only change one concentration of all the reactants and keep the rest constant. And we observe how the reaction rate changes with the change in concentration. Now let's look at the effects of concentration on reaction rates. We can rationalize the dependence of reaction rates on concentration by considering the illustration in this figure. The rate law indicates that the rate is the first order with respect to NO and O3, ozone. For a reaction to occur, there must be a collision between reacting species, NO and O3. In the first flask, the rate depends on the collision as indicated over here. Moving to the second flask, the concentration of NO is doubled. So the probability of the collision between NO and O3 molecule also doubles. Then moving to the third flask, we now double the concentration for O3 as well. The probability of the collisions increase by another factor of 2. So now we have 4 times greater than in the first flask. Similarly, increasing the concentration of NO and O3 by a factor of 3 each compared to the first flask increases the probability of collision by 3 squared times, or 9 times. Let's look at another example. Write the rate law and calculate the rate constant K for the reaction below using the following data. So let's analyze the data over here. When we want to determine the rate law, the generic rate law is rate times rate constant, NO raised to M and H2 raised to N. To determine M, we will need to make sure NO concentration is changing while H2 concentration is kept constant. So when we look at that, to determine M, it would be experiment 1, which has H2 kept constant and NO concentration changing. So this would be experiment 1 and 3. And when we want to determine the reaction order with respect to H2, we need to make sure H2 concentration is changing while all other concentrations kept a constant. So that would be experiment 1 and 2, because for experiment 1 and 2, the concentration of NO does not change, but the H2 concentration is doubled. So to determine N, it would be experiment 1 and 2. When we compare trials 1 and 2, the H2 concentrations doubles from 0.140 to 0.280. And the rate also doubles, as you can see from this too. The rate changes as many times as the concentration change. For this reason, the rate order or the reaction order with respect to H2 is 1, or N is 1. When we compare trials 1 and 3, the H2 concentration is kept constant, and the NO concentration is doubled. As we can see, the initial rate is quadrupled. For this reason, the reaction will have a reaction order with respect to NO, that is number 2. For this reason, the generic rate law can be rewritten as rate equals K times NO squared times H2 concentration. And the overall reaction order is 2 plus 1. So 2 plus this 1. So that's the overall reaction order. That's 3. And we substitute the data for any trial. For example, if you substitute the trial number 1 in, that's the whole set of data. The rate and the concentration of NO, then concentration of hydrogen, we can calculate K, which is determined to be 15.4 m raised to negative 2 and per second. So far, through 2 examples, we have gone over the details how to experimentally determine the rate law. By determining the rate order with respect to each reactant. In this method, a series of experiments are designed in which a pair of experiments will only have one change in concentration, while the rest of concentrations will be kept constant. We observe how the initial rate changes with the changing concentration. Then we can determine the rate law with respect to that reactant concentration. The rate constant can be calculated by substituting all the numbers from any trial. Now let's have a look at the integrated rate law. In the integrated rate law, it's the mathematical expression describing the change in the concentration of a reaction with time. For example, ozone decomposition to oxygen and the oxygen atom is the first law reaction. So the generic rate law would be rate equals K times the current concentration. When we do an integration of this particular rate law, then you will have these 2 equivalent equations for the first order of reaction. These 2 are equivalent, which tells you the logarithm of the ratio of current concentration. This T means current concentration. This 0 means initial concentration. In this rate law, if you plot the natural log of the current concentration versus time, it will give us a straight line, like the log of current concentration versus time. This gives us a straight line, and the slope will be negative K, and the y-intercept will be log of initial concentration. Let's look at this example in great detail. When you plot the concentration versus time, it gives us a curved line. But when you plot the logarithm of concentration versus time, it gives us a straight line. For this reason, the reaction is the first order. reaction. An important parameter in reaction kinetics is the half-time, which is the time needed for initial concentration of a reactant to decrease by a half. Half-time or half-life is inversely related to the rate constant. The larger the rate constant, the shorter the half-life. The half-life of a first-order reaction, T1/2, is natural log of 2 over rate constant K. As you can see, for first-order reaction, the half-time or half-life is independent of initial concentration. Clearly, the reaction proceeds rapidly, with the initial concentration decreasing by a half from 16 to 8 in the first 1 second interval. And note in the exact next 1 second interval, from 1 second to 2 seconds, the concentration decreases from 8 to 4. Although the initial concentration changed from 16 to 8 for the second interval, you noticed the half-life or half-time does not change for the first order. This is not true for the 0th order or second order reaction. As we just indicated, the half-life of a first order reaction is 0.693 over K, because natural log of 2 is actually 0.6932. So you can also write it as half-life is natural log of 2 over K. They are exactly the same. Let's work on another problem for the first order reaction. The radioactive isotope decays by first order kinetics and has half-life of 14.3 days. How long does it take for 95.0% of a sample of P32 to decay? So first, we know the half-life is 14.3 days. According to T1/2 equals 0.693 over K, we will be able, because half-life is known, so we can calculate the K. With the K, we will be able to calculate how much time it takes for 95% of the sample to be consumed. So let's work on this problem. First, according to T1/2 or half-life is 0.693 over K, so we can figure out K is 0.693 over 14.3. So we find out the K. According to the first order integrated rate law, which tells you log current concentration over initial concentration equals negative times KT. So we substitute the numbers in because 95% is consumed. So the current concentration would account for 0.05 if the initial is 1.00, okay, which is 100%. And we also substitute the K in after we do the calculation. T is 61.8 days. As we can see in this question, first we use the known half-life to calculate the rate constant K. Then use the rate constant K and substitute this in the first order reaction. We can calculate the time it takes to consume 95.0% of the sample. Now let's switch gear and look at the second order reaction. For the second order, the instantaneous rate law or differential rate law or simply rate law is rate equals K times concentration squared. If you do the integration, you will have the inverse of the current concentration equals K times T plus the inverse of initial concentration. If you plot the inverse of concentration versus time, it will give you a straight line. So inverse of the current concentration versus time, and the slope is K in this case. That will be a positive slope. And the y-intercept over here will be the inverse, it will be this one, will be the inverse of initial concentration. For the second order reaction, the half-life is inversely proportional to the initial concentration. In other words, the greater the initial concentration, the less time it takes for half of the substance to be consumed. We can also rewrite the half-time of 1 over K times the inverse of initial concentration. As we can see, obviously, when initial concentration increases, it takes less time to reach half-time. For the second order reaction, as we can see, when we plot the inverse of current concentration versus time, it gives us a straight line. If you do the logarithm of current concentration versus time, it gives us a curve. Let's look at the zeroth order reaction. For zeroth order reaction, rate is K. This comes from the rate equals K times the concentration raised to 0. And anything raised to 0 will be 1. So that's why for the zeroth order, rate does not change with concentration, or rate equals rate constant. When you do the integration based on the generic rate law, you will have current concentration equals negative kT plus initial concentration. Similarly, if you plot this concentration term versus time, so that's the current concentration versus time, and you plot it, the slope apparently is the negative K. So that's the slope. We plot this thing, you will find out the y-intercept is initial concentration. As we just mentioned, the slope is negative K over here. The half-time for the zeroth order reaction is, you should have a subscript 0 here because it's initial concentration. It's initial concentration over 2K, or you can rewrite it as 1 over K times initial concentration over 2 as the half-time. As you can see over here, for the zeroth order reaction, when the initial concentration increases, the half-time also increases. We have everything summarized in your problem set. Please work on your problem set carefully as well to have more practice. We have already examined how concentrations of a reactant species affect the rate of the reaction, and how this is reflected in the rate law by reaction order. But what determines the value of K in the rate law? As the molecules collide, bonds in reactants are broken, which allow new bonds to form to yield the products. The collision between the molecules must be of sufficient energy to break the bonds in reactants, or no reaction occurs. The temperature of a reaction will affect the energy of the collisions because the kinetic energy of the molecules is directly related to the temperature. As T increases, we would expect the reaction rate to increase since kinetic energy of the molecules increases. The minimum amount of energy that is required to break the bonds in the reactants, leading to the formation of the product, and this is so-called activation energy. And these two factors, temperature and activation energy, are reflected in the rate law by incorporation into the rate constant. And this is so-called Arrhenius equation, which incorporates both factors, activation energy and the temperature, into the rate constant expression. And rate constant is a lowercase k. The R is the gas constant in joule per mole per K, or in another word, you should use 8.314 joule per mole per K. That's the number you should use for the gas constant. Temperature is in Kelvin, and A is so-called a collision frequency factor. That's so-called a frequency factor. It includes the frequency of collisions and the orientation factor. Both these equations are Arrhenius equation. And the first one, since it's in the exponential form, so we call this exponential form of the Arrhenius equation. The logarithm one is so-called a linear form, because when you plot the natural log of rate constant against inverse of temperature in Kelvin, we have a straight line. So if you plot natural log of K versus inverse of T, you will have a straight line, and the slope is negative activation energy over R. The y-intercept is natural log of frequency factor A. Because when you plot the natural log of K versus inverse of temperature, gives us a straight line. So we call this log form, or we can call this linear form. If you look at our problem set, you will see a third form, which is called a two-point form. And that is the log K2 over K1 gives us negative EA over R, 1 over T2 minus 1 over T1. And this is so-called a two-point form. We have more exercises in the problem set, so please have a look at it. We can illustrate the role of activation energy by considering the relative internal energies in the reactant and the products. And this curve you see over here is so-called a reaction energy profile. In the highest, or the apex, in the highest point, that's so-called activated complex, or sometimes we also call this transition state. The energy that is required to overcome the energy barrier is called the activation energy. The activation energy actually starts from the starting point of reactants to the highest point of that particular peak. If you have a multi-step, for example, in another energy profile or reaction profile, you have two peaks over here, and the activation energy, you will have two activation energies. The first one starts with the starting point. So the first activation energy starts with the foothill, that's EA. The second one will start with the middle, that's right over here, that's where it starts. The second activation energy. The bigger the activation energy EA, the fewer collisions you would expect to have sufficient energy, and the slower the reaction rate. In other words, when activation energy increases, the rate constant will become smaller. Therefore, the reaction rates will decrease as well. We can rationalize the effect of temperature on K by recalling how kinetic energy is related to temperature. Consider the distribution of collision energy at two different temperatures as illustrated, and that T2 is greater than T1. On this graph, the dashed line represents the activation energy. The minimum collision energy required to form the activated complex, or so-called transition state, to form the product is the activation energy. As the temperature increases, the curve flattens out. T2 is greater than T1, remember. But when you look at the fraction of collision of the molecule, the fraction of the molecules that have enough energy or energy greater than EA increases. That's why the reaction rate increases. To understand the role of collision orientation, let's look at this example. Consider ozone reacting with nitrogen monoxide. Ozone and nitrogen monoxide should be arranged in such a way that the blue, which is nitrogen, and oxygen is represented in red. So nitrogen should be facing ozone. This will form the so-called activated complex, or so-called transition state. Then you have the bond being formed and being broken, forming this product as you see over here. However, if oxygen is pointed toward the ozone, the reaction will not happen. So this collision, no matter how hard they collide with each other, no reaction will happen, and this collision is ineffective collision. This dependence on collision orientation is reflected in the frequency factor A, and depends on the probability of the collision occurring in an appropriate orientation to yield the products. The orientation factor is part of the frequency factor in the Arrhenius equation. Orientation factor is part of the frequency factor A. Let's consider the energy profile for the reaction between nitrogen monoxide and ozone. As illustrated in this figure, the activation energy for this reaction is very small, which translates to a very large value for the rate constant according to Arrhenius equation. The reaction is very fast. Now consider the energy profile for the reverse reaction between NO2 and oxygen gas. The activation energy now is really big. If we look back, the EA for the forward reaction is very small. For the reverse reaction, the products will become the reactants. Reactants will become the products. So the activation energy for the reverse, this is EA for reverse reaction, which is represented right over here. That's exactly the same thing. As you can see, the activation energy for the reverse reaction is extremely high. This indicates the reverse reaction is very, very slow. The forward reaction is much faster than the reverse reaction. Another useful application of Arrhenius equation is that it allows us to determine the activation energy of the reaction. You consider again the log form, or so-called the linear form, of the Arrhenius equation. Natural log of K equals the slope times inverse of T plus natural log of K. When you plot natural log of K versus inverse of T, So when you plot this term against inverse of t, the slope will be negative EA over R. So that's the slope over here. That's the slope. And log A, that's the y-intercept. Y-intercept. That's the y-intercept here. For more details of this type of calculation, please refer to your problem set. We previously briefly talked about the two-point form. Two-point form comes from the log form or linear form under two different conditions, temperature 1 and K relationship, temperature 2 and K relationship. So you subtract these two equations, you will come up with so-called two-point form. Of Arrhenius equation. We have one more example on the problem set. Please check it out. So far, we have examined how the rate law defines the relationship between reaction rate and the concentration of reactants. We have also discussed how the rate law can be determined experimentally and how the value of the rate constant can provide insight into important parameters related to the reaction, such as the activation energy. But why are some reactions first order and others second order or zeroth order? To explain this, we need to examine what actually happens at the molecular level during the reaction by proposing a reaction mechanism. A reaction mechanism is actually a set of steps that describe how a reaction occurs at the molecular level, and this must be consistent with the rate law for the reaction. The steps in the mechanism are so-called an elementary step. This represents the molecular level view of a single process taking place in the chemical reaction. And that's the smallest possible step that can happen in the real situation. The intermediate is the species produced in one step of reaction and consumed in the subsequent steps. Molecularity tells you the number of species, for example, ions, atoms, or molecules that are involved in an elementary step. Consider the decomposition reaction of nitrogen dioxide to nitrogen monoxide and oxygen. We may propose this reaction takes place in two separate steps. Step 1, two molecules NO2 react to produce NO and NO3. Step 2, NO3 molecule decomposes to NO and O2. There are several things to note about this mechanism. First, NO3 produced in step 1 is consumed as a reactant in the second step. For this reason, NO3 is an intermediate. It appears as the product of the first step and is consumed as a reactant in the second step. In addition, the first step is bimolecular because two molecules NO2 are involved, and the second step is unimolecular. Finally, if we add the two steps together and cancel the intermediate species, we obtain the balanced chemical equation. Another point of interest is that we can write the rate laws based on the molecularity of elementary steps or the proposed stepwise mechanism. For example, step 1, which is an elementary step, the rate for this step can be written as K1, 1 means step 1, NO2 squared from the reactants. And for the rate for step 2, it will be K2 times NO2, because you only have a unimolecular process. One molecule is involved. So you raise this to 1, or you don't have to write that 1. However, please note, we cannot do this for the overall balanced reaction because we do not know exactly what is happening at the molecular level. For example, based on overall reaction, you cannot simply say the rate equals K times NO2 squared, although the observed rate law happens to be the same, but the rate law cannot be directly read out from the overall reaction, even if the observed rate law happens to agree with the rate law that is written out. This cannot be written directly. This is a wrong way to do it. I'm going to say it for one more time. The observed rate law happens to be the same as what you would have read out of the overall reaction, but you cannot read the rate law directly from the overall reaction. Rather, you can do that for the elementary steps, because each elementary step represents the real reaction that is happening. If we cannot write the rate law based on the overall reaction, how do we know if this mechanism is feasible? To satisfy this requirement, the mechanism must be consistent with the experimentally observed rate law. To address this issue, we must identify so-called rate determining step, or RDS, which is the slowest step of all proposed stepwise mechanism. Since the reaction cannot proceed faster than the slowest step, or the rate determining step, the rate law obtained from the slowest elementary step will be exactly the same as the experimentally observed rate law, although it might be written in different forms. Let's examine the reaction energy profile for the proposed reaction mechanism. Step 1 has a large activation energy, as you see over here. Very large activation energy. Step 2 has a smaller activation energy. This tells us step 1 is slower than step 2. For this reason, step 1 is the rate determining step. If the step 1 is rate determining step, we go back and we know the reaction rate is based on the first step, which is the slow step, or so-called rate determining step. That's why for this particular reaction, because step 1 is the slow step, the reaction rate for overall reaction is always the same as the rate law for rate determining step. In this case, the rate law for rate determining step is K times NO2 raised to 2. And the reason is because when you look at this, it's because of this. Since the experimentally observed rate law, or the observed rate law, agrees with the proposed rate law according to this mechanism, that means this proposed mechanism is reasonable, or it could be correct, but it doesn't exclude other possible mechanisms. What about the reverse reaction? We previously determined that experimentally observed rate law for this reaction was rate equals K times NO squared and the concentration of O2. How do we rationalize this based on the previously proposed mechanism? When we look at the previous reaction, which is a reverse reaction of the one we are studying here, the step 2 in the previous mechanism would be the step 1 in the reverse direction, and step 1 in the previously proposed mechanism will become the step 2 in the reverse direction. And we can write the reaction rate based on the reactants because they are elementary steps. Remember, in the previously studied reverse reaction to this one, step 1 is the rate determining step. So the step 2 over here will actually be the rate determining step. Because when you look at the reverse direction, this reaction is the slowest step. So the first step is such a fast step. The second step is the slow step over here. Do remember, the reaction rate will be the same as the rate determining step. In other words, rate for the overall reaction will be the same as step 2 or rate 2. That means K2 NO3 times NO concentration. But do remember, this NO is a concentration that does not appear in this overall reaction. As you see over here, NO3 is not a part of the overall reaction. Rather, this is an intermediate. We must convert the intermediate concentration to any concentration terms that is part of the overall reaction. It must be part of the overall reaction. Any concentration terms inside the rate law. For this reason, we have to find the intermediate concentration NO3 and try to relate it to the other concentrations. So how do we do it? The key is any steps or any faster steps before the rate determining step, they are considered at equilibrium or so-called reversible. In this way, we do know any step that is at equilibrium has the rate for the forward reaction and the rate for the reverse reaction exactly the same. The rate for the forward reaction for the first step or the fast step is Kf NO times that of O2, because when you look at this first reaction, you have a NO and O2 as a reactants. That's why Kf times NO times O2, this gives you forward reaction rate. Okay. And for the reverse reaction, for the first step reverse reaction, NO3 would be the reactants for the reverse reaction. And Kr is the rate constant for the reverse reaction times the concentration of the reactant for the reverse reaction. These two are the same. Through this equation, we can find out the intermediate concentration NO3 equals this. Let's call this equation 1 and call this one equation 2. So we're going to substitute equation 1 into equation 2. So rate will be K2. Now we're going to substitute NO3 into that equation 2. It will be Kf over Kr times NO O2. So this is NO3 concentration. And then we have NO left. We're going to multiply NO. Okay. So when you rewrite it, NO terms are the same, so we put it together. So this rate will be K2 times Kf over Kr times NO squared times O2. And as you can see, this equation is consistent with what you have observed over here. They are consistent. For more examples, please have a look at your problem set. Ozone in photochemical smog is an irritant and it contributes to the destruction of plants. In the stratosphere, however, it is useful because it absorbs UV radiation. In 1974, two chemists, Sherwood Rowland and Mario Molina, predicted that the presence of volatile organic compounds called the chlorofluorocarbons, or CFCs, would contribute to a significant depletion of the stratospheric ozone layer. This prediction was later supported by experimental evidence that demonstrated a thinning of ozone layer and the appearance of an ozone hole over Antarctica. This phenomenon is illustrated in this figure, as you can see over here. The ozone hole increased substantially from 1980 to the year of 2000. This trend led to an international agreement called the Montreal Protocol, which limited the production of CFCs. Since then, ozone levels have started to increase and the ozone hole has decreased. But it will take a long time for the levels to recover to pre-1980 levels because of the persistence of these compounds in the environment. Photodecomposition of ozone is a naturally occurring process in the stratosphere. With the proposed two-step mechanism shown, the net reaction is the conversion of ozone to oxygen gas. The activation energy for the rate determined step, the second step, is 17.7 kilojoule per mole. How do CFCs contribute to the destruction of ozone layer? These compounds are volatile and extremely stable and remain in the atmosphere for long periods of time so that they ultimately can disperse up into the stratosphere. In the stratosphere, these compounds encounter UV radiation of sufficient energy to cause the decomposition and produce chlorine atoms. These chlorine atoms then interact with ozone in a two-step mechanism, step 2 and step 3, thus cause the destruction of ozone layer. Please note the overall reaction is the same as that for the natural photodecomposition of ozone from the previous slide, as you can see over here. The net reaction for the natural process and the net reaction for the catalyzed reaction. But the difference is that the activation energy for the chlorine catalyzed reaction is 2.2 kilojoule per mole, which is much smaller than the previously determined 17.7 kilojoule. So the catalyzed process is much faster according to Arrhenius Equation. The two reaction pathways for the decomposition of ozone are illustrated in this picture. The energy profiles, as you see, for the natural process in blue. The catalyzed reaction has the first step as the rate determined step, as you can see in the red curve over here. And the activation energy is only 2.2 kilojoule per mole. For the natural process, which is also a two-step procedure, the second step is the rate determined step with activation energy of 17.7 kilojoule per mole, which is much bigger than that of the catalyzed process. Another example of the action of a catalyst is the catalytic converter that we mentioned at the beginning of this chapter. Catalytic converters are included in all automobiles manufactured in the United States in order to decrease the production of nitric oxides, such as nitrogen monoxide. The large surface areas of metal clusters in the honeycomb-like structure of the catalytic converter allows for rapid oxidation reduction of the nitric oxide species and speeds up their conversion to non-polluting nitrogen and oxygen. Because of the catalyst is in different phase than the reactants, the catalyst is the solid phase and the reactants the gas phase. So this is an example of a heterogeneous catalyst. The catalytic surfaces in catalytic converters are capable of catalyzing a variety of reactions. Catalysts are also useful in biochemistry. In contrast, however, these biochemical catalysts are highly selective and typically only work for a very specific reaction. Such biochemical catalysts are also called enzymes, and the substances with which they act catalytically are called substrates. Enzymes are very important in metabolic pathways, sequences of reactions that are responsible for the synthesis of complex materials from the simpler compounds. The specificity of enzyme is due to the shape and structure of an active site, which is tailored to interact with a specific substrate. Using molecular recognition strategies discussed previously. Enzymes are also used in many industrial applications because they convey the chiral specificity to produce the enantiomerically pure products. This practice of using enzymes to catalyze reactions on a large scale is called the biocatalysis. As you can see, the catalyzed route, indicated in red, has lower activation energy. Please remember, the catalysts, they do not change before and after the reaction, but they do participate in the process to lower the activation energy, thus changing the route of the chemical reaction. But the starting material and the products will be the same. So that's it for today. For more exercises, please refer to the detailed answer key of your problem set. See you next time. Bye.